the prototype problem that we are going to look at today. So we have this problem involving the P Laplacian operator, and we on the right hand side we have three terms. The first term has the same homogeneity as the P Laplacian, so it's of the order P minus 1, and then we have a term of order less than P minus 1. The sigma is less than P, and then we have a term of order higher than P minus 1. This Q is bigger than P. So problems like these are generally referred to as problems with combined nonlinearities. And the term Q can be up to the critical exponent np over n minus p if p is less than n, and no restrictions on Q if p is greater than or equal to n. And lambda and mu are basically two parameters, two positive parameters. So the basic result that we want to prove here is that for all positive lambda, this problem has at least two non-trivial solutions if mu is small enough. So let me denote by lambda 1 the first directly eigenvalue of the P Laplacian on omega. So this is positive. And if lambda is between 0 and lambda 1 and mu is positive, then you can produce a pair of non-trivial solutions by using a local minimization argument and the mountain pass theorem. So what you do is you produce an ordered pair of positive sub and super solutions, and then you can get a local minimizer between those sub and super solutions. And then you apply the mountain pass theorem to get a second non-trivial solution. So the local minimizer will be at a negative energy level, and the mountain pass point will be at a positive energy level. So this was an argument that was first used by Ambrosetti, Brazis, and Cerami in their 1994 paper. And after that, many people have extended this to related problems like the P Laplacian. The original paper of Ambrosetti, Brazis, and Cerami considered the Laplacian. So that's the case where P is equal to 2. And it was followed by other people extending this to P different from 2. So here are some examples of papers giving results on this problem for the P Laplacian, starting with Azzaroro and Azzaroro, Alonso, and Manfredi in 2000. So the case that lambda is less than lambda 1 is more or less settled. And this talk is mainly about the case where lambda is bigger than or equal to lambda 1. So in this case, the variational functional no longer has the mountain pass geometry. And as far as I know, there are no results, there are no multiplicity results for this problem available in the literature for that case. So I'm going to present a linking theorem based on a cohomological index theory that can basically capture the geometry of the functional when lambda is bigger than or equal to lambda 1, and still produce a pair of non-trivial critical points for all positive lambda, provided that mu is sufficiently small. But these critical points are not going to be minimizers. They're not going to be local minimizers or mountain pass points. They are going to be higher critical points in the sense that they both have a non-trivial higher critical group. So let me just recall the definition of critical groups quickly. So suppose you have a C1 functional E defined on a Banach space, and suppose U0 is an isolated critical point of E. So the critical groups of E at U0 are in dimension Q are defined to be the relative singular homology groups group of the pair EC and EC minus U0, where EC is the sublevel set where the functional is less than or equal to the critical value corresponding to U0. So these critical groups basically measure the change in the topology of the sublevel sets when you pass through the critical point U0. Okay, so now let me describe the main result here, which is the abstract critical point theorem. So suppose W is a Banach space and M is a bounded symmetric subset of W minus 0 that's radially homeomorphic to the unit sphere. So this means that if you take the radial projection onto the unit sphere and restrict it to M, that's a homeomorphism onto the unit sphere. So in that case, we could write down what the radial projection onto M is in terms of the radial projection onto S, the unit sphere. So if you first radially project onto the unit sphere and then pull it back using the inverse of the restriction to M of the projection onto the unit sphere, you get the radial projection onto to M. So we will make use of this projection pi M. And then I will denote by IA the Z2 cohomological index of Fadel and Rabinowitz for a symmetric subset A contained in W minus the origin. Okay, so with that, let me describe the abstract critical point theorem. So suppose you have a C1 functional on W and two disjoint closed symmetric subsets of M with the property that the index of A0 and the index of the complement of B0 in M are the same and their common value is finite. And then we are going to use these two sets A0 and B0 to construct a linking structure. So suppose there is a W0 in M minus A0 and numbers R, little r, which can be 0 or positive, and a row and R in that order, and two real numbers A and A less than B. And we are going to describe these sets A1, A star, B star, A, and B. So let me show you what these sets would look like in a picture, roughly speaking. So for example, suppose M looks like a sphere, and so in this picture, these two shaded areas on M denote the set A0, and this band is the set B0. And then again, the requirement is that the index of A0 and the index of the complement of B0 are the same. And then we take this other point W0 on M, and we define this set A1. So the A1 is the set of, so here's how you construct the set A1. You take all line segments joining points on A0 to W0, and you project those line segments onto the set M radial using the radial projection pi M. So using this set A1, now we are going to construct two sets, A and B, that link in a sense that I will describe soon. So what you do is the set B is basically a scaled copy of B0. So this B0 is basically, I'm sorry, this set B is basically set B0 scaled, dilated by rho. And then the construction of the set A is a little more complicated. So here's what you do. You take the set A1 and you scale it by the by little r. So you get this little scaled copy of A1, and little r is less than rho, so that will be inside the band B. And then you also take a scaled copy of A1, scaled by capital R. So that's this set in the front. And this set will be outside of B because capital R is bigger than rho. And then you look at the two copies of A0 on these two sets, the one in the rear and the one in the front. And so you have these two scaled copies of the set A0 on those two sets, and you join the corresponding copy, points on those two copies by line segments. So this part and that part are made up of the line segments joining points on the two copies of A0 that are on the front arc and the rear arc. So this is the setting. So I have described those sets here, and with that, here's the so here are the main assumptions on E. And also we have two sets. These two sets, A star and B star. So A star and B star are basically filling in the two sets A and B. So B star is just the set of all line segments joining points on B to the origin, and A star is the set that fills in between this set A. So basically what you do is you look at this rear copy of A0 and the front copy of the rear copy of A1 and the front copy of A1, look at their corresponding points and join the corresponding points by line segments. So A star is the set filling in this set A by those line segments. Okay, so with that, here are the assumptions on the functional. We assume that on the set B star, E is bigger than A. So on the set that's filling in B, the functional is bigger than A. And then we assume that on A and B, the values of the functional are bounded away from each other. So meaning that the sup of E on A is strictly smaller than the inf of E on B. And finally, we assume that on the set A star, which fills in the set A, the functional is strictly smaller than B. So the sup of E on A star is less than B. And then we also assume that the functional satisfies the Palais-Mail condition at all levels between A and B. Then the conclusion is that E has a pair of critical points, U1 and U2, with the critical value of U1 between the inf of E on B star and the sup of E on A. So this will be a critical point with energy less than the supremum of E on A, and the second critical point will have its critical value between the infimum of E on B and the supremum of E on A star. So it will have energy bigger than or equal to the infimum of E on B. And then if in addition, if you assume that E has only a finite number of critical points with critical values in the interval from A to B, then you can choose U1 and U2 in such a way that the kth critical group of U1 is non-trivial and the k plus first critical group of U2 is non-trivial. And then remember that this k is the common cohomological index of A0 and the complement of B0 in there. Okay, so this is the abstract critical point theorem, and the proof of this is based on the notion of the cohomological linking. So let me quickly recall the definition of cohomological linking. So suppose you have two disjoint non-empty subsets A and B of a Banach space W, then we say that A links B cohomologically in dimension K if the inclusion of A in the complement of B induces a non-trivial homomorphism between the cohomology in dimension K. So this inclusion induces this homomorphism between the reduced cohomology groups in all dimensions. So it will be from the reduced cohomology of W minus B to the reduced cohomology of A. And the assumption is that this homomorphism is non-trivial in dimension K. And if that's the case, then we say that these sets link cohomologically in dimension K. So the proof of the theorem is based on this new linking structure. So basically you show that this set A links the set B cohomologically in dimension K, and this is the main step in the proof of the theorem. And once you have that, then you can use the assumptions that we made about the values of the functional on these sets to produce two pairs of regular values of the functional with non-trivial relative cohomology. So you produce a pair of regular values of E with reduced the relative cohomology non-trivial in dimension K, and then you produce another pair with the sublevel sets having relative cohomology non-trivial in dimension K plus 1, and then these two give you the existence of U1 and U2, and they also give you this additional information about the critical groups when you have isolated critical points, when you only have isolated critical points. Okay, so with that, let me go back to our the P-Laplacian problem and then indicate how to apply this abstract critical point theorem to get a pair of non-trivial solutions of this problem. But rather than doing this just for the P-Laplacian, I will do this for a general class of problems that model the P-Laplacian problem that I mentioned at the beginning. Because this type of result applies not only to the P-Laplacian, but to any problem, any operator that has the same structure as the P-Laplacian. For example, the fractional P-Laplacian or Kirchhoff type non-local problems. So let me prove an abstract multiplicity result. So our setting will be in a uniformly convex Banach space W with dual W star, and I will prove a multiplicity result to a class of potential equations. So let me recall that an operator, a continuous operator from W to its dual is a potential operator if it's the Frechet derivative of some C1 functional on W. So this C1 functional capital H is called a potential for H. So capital H prime is H. So we will consider this nonlinear operator equation. You have two operators AP and BP. So now first example, this AP is the P Laplacian, the BP is the u to the power p minus 1, and then you have two other potential operators. The first one will be of lower order than p minus 1. The second one will be of higher order than p minus 1. Okay, so these are all potential operators, and lambda and mu are positive. So here are our assumptions on all these operators. So first of all, AP is assumed to be p minus 1 homogeneous and odd, meaning that this relation holds for all u in W and t in R. And then we assume an inequality of the holder type. So APUB is assumed to be less than or equal to u to the p minus 1v. And the equality holds if and only if u and v are scalar multiples of each other. So in particular, APUU is the norm of u to the power p. And again, both the P Laplacian and then the fractional P Laplacian would satisfy these assumptions. And then BP is also assumed to be p minus 1 homogeneous and odd, and is assumed to be positive for u positive, and also assumed to satisfy a holder type inequality. This holder type inequality. And of course, u to the power p minus 1 does satisfy this. And finally, it's assumed to be a compact operator. Okay, so those are the operators A and B. And then, so here are the assumptions on F and G. So let's denote by capital F the potential of little f with F0 equals 0. You can always achieve this by just subtracting F0 from F. That will give you another potential with values 0 and 0. And this is assumed to satisfy this limit. So f of tu divided by t to the power p goes to 0. Goes to positive infinity as t goes to 0. So this basically means that the potential f goes like a power that's smaller than p. So in our example, we had sigma less than p. So the u to the power sigma minus 1 will satisfy this. And the limit is assumed to be uniform on compact subsets of W minus 0. And it's assumed to be positive except at the origin. And F is assumed to be bounded on bounded subsets of W. And here are the assumptions on G. So again, denote by capital G the potential with capital G of 0 equals 0. And this is assumed to go to 0 when divided by the norm of u to the power p when u goes to 0. So this is basically saying that G is of a higher power than p near the origin. So in our example, this is something like u to the power q, where q is bigger than p. And G is also assumed to be positive except at the origin and bounded on bounded subsets of W. And and this is the main assumption on G at infinity. So G of tu over t to the power p is assumed to go to positive infinity when t goes to positive infinity. Again, uniformly on compact subsets of W minus 0. So again, in our example, this is a higher power than p. So when at infinity, it goes to infinity. So the solutions of this equation are the critical points of this C1 functional. The first term is the potential of the operator AP, and the second term is lambda times the potential of the operator BP, and then you have the two potentials of F and G, and you see that if you differentiate this, E prime is exactly what you get when you bring all these terms of the equation to the left-hand side. Okay, so with that, here's the main multiplicity result for this abstract equation. Assume that A1 through G4 hold, and you have the PSC condition for all C. And then if lambda is positive, depending on lambda, there is a mu zero such that this equation has two non-trivial solutions, U1 and U2, for all mu between 0 and mu 0. The first solution has negative energy, and the second one has positive energy. And let me just indicate how the abstract critical point theorem is applied to get this multiplicity result. So the proof is going to involve the nonlinear eigenvalue problem, APU equals lambda VPU. So here's the variational formulation of this eigenvalue problem. Let's denote by M the sphere of radius p to the power 1 over p in W. So this is it's basically a bounded complete symmetric C1 Finchner manifold. It's radially homeomorphic to the unit sphere. So it fits into the setting of the abstract critical point theorem. And then the eigenvalues of this problem coincide with the critical values of this functional psi, given by p over basically this is the 1 over the potential of the operator Vp. And then you can construct a sequence of eigenvalues using a minimax scheme based on some index theory. The standard way to do this is to use the genus of Krasnoselski as the index. But if you use the critical values based on the genus, you don't get enough information about the indexes of the sublevel sets to apply the abstract critical point theorem. So what we are going to do here is to construct the sequence of eigenvalues based on the cohomological index. So let's denote by capital F the class of symmetric subsets of M, and by Fk the sets with index at least k, and you set lambda k to be the min max based on this class of sets Fk. And then one can show that this is an unbounded and increasing sequence of eigenvalues. The first eigenvalue is positive, etc. And this sequence of eigenvalues based on the cohomological index was first introduced in this 2003 paper in topological methods in nonlinear analysis. Okay, so now let me denote by psi super A the sublevel set where psi is less than or equal to A, and by psi sub A the superlevel set where it's bigger than or equal to A. Then, so here's what you get from using the cohomological index. If lambda k is less than lambda k plus 1, then the index of the sublevel set where psi is less than or equal to lambda k is equal to k. And also the index of the complement of the superlevel set where psi is bigger than or equal to lambda k plus 1 is also k. And you see that this is the type of assumption that we had for the sets A0 and B0 in the abstract critical point theorem. So that assumption was based on this observation. But to apply the critical point theorem, then we also need to replace this psi lambda k with a set that's a little more regular. So here's a key lemma in the application. So the lemma is that if lambda k is less than lambda k plus 1, then the sublevel set psi lambda k has a compact symmetric subset A0 of index k. So this psi lambda k in general need not be compact, but you can construct a subset, a compact symmetric subset of the same index as psi lambda k, and that this will be useful. So here's how the abstract critical point theorem is applied. If lambda is between 0 and lambda 1, you take the set A0 to be the empty set and B0 to be the whole sphere M. So in this case, the index of A0 is 0, so is the index of the complement of B0. And if lambda is bigger than or equal to lambda 1, then lambda is between lambda k and lambda k plus 1 for some k bigger than or equal to 1. And then you take A0 to be the compact symmetric subset of psi lambda k with index k, and B0 to be the superlevel set where psi is bigger than or equal to lambda k plus 1. And then, so we have this relation, which is the main assumption in the theorem, and you can then just apply the abstract critical point theorem to get the multiplicity result. Okay, so let's see how this is applied in our prototype example. So let's go back to this this original problem, and I will replace the term u to the power sigma minus 1 with a more general nonlinearity. So this f is something like u to the power p minus sigma u to the power sigma minus 1 with sigma less than 1, but it's not assumed to be odd in u. If it's odd in u, then you can get multiplicity results using the symmetry. The functional will be even, and then you can use other results for critical points of symmetric functionals. So here we are not assuming that. These results does not involve any symmetry. So symmetry does not play any role in these results. So this this little f is it goes like t to the sigma minus 1 near 0, and its primitive is assumed to be positive except at t equal to 0. And then we assume a growth condition on f. So we assume that its growth is subcritical, is lower than the power q, and then q can be up to the critical exponent np over n minus p if p is less than n. And then the solutions of this problem coincide with the critical points of this functional. So this is the variational functional associated with our problem. So the first result here is for the subcritical case. So suppose q is less than p star. If p is less than n, no restrictions. If p is bigger than or equal to n, and lambda is positive, then applying the multiplicity result for the abstract operator equation, we get two non-trivial solutions, one with negative energy and one with positive energy for all small enough mu. And so basically you apply the abstract result with these choices of operators. So AP in this case will be the operator from W1P0 to its dual given by this equation. So APU acting on V is this integral, and the other operators are defined similarly. And then so basically the operator equation is the weak formulation of the P-Laplacian equation. And also for the semi-linear case, p equal to 2, this result was actually recently obtained in this paper with Candito and Marano to appear in Communications in Contemporary Mathematics. But the method used there was very different. So there, the operator is linear. The Laplacian is a linear operator, so it has linear eigenspaces. So you can do linking arguments based on linear subspaces. But for p not equal to 2, this just doesn't work because it does not, the p Laplacian for p different from 2 does not have linear eigenspaces, so you need something based on the sublevel sets, like in the abstract critical point theorem here. Okay, so here's another application of the abstract multiplicity result. Suppose we consider this the Kirchhoff type non-local problem. So here we are looking at a subcritical problem. So since omega is a bounded domain in Rn, n is 1, 2, or 3, and this q is between 4 and 6. So in dimension 3, 6 is the critical exponent, so it's assumed to be less than 6 if n is 3, and no restrictions above if n is 1 or 2. And again, f is the same type of function as in the earlier example. So it's so f goes like t to the power sigma minus 1, where sigma is less than 4, and q is bigger than 3. No, so q is bigger than 4. So here p is basically 4, and this is the p minus 1 term. It is the term that's of a lower power, and this is the term that's of a higher power. So here, and then by the way, this is a non-local problem because you have this this integral in front of the Laplacian. So at each point, this equation depends on the values of u on the whole domain, making it a non-local problem. But this problem has pretty much the same structure as the P Laplacian equation that we looked at. So a similar result holds for this. So here's the variation of functional, and the result is that if you assume what we just assumed about P and about Q and R, then in the subcritical case, again you can find two solutions, one at a negative energy level, one at a positive energy level, if the parameter mu is small. And again, there are no restrictions on lambda. So I mean, so if you compare this functional with the functional for the P Laplacian, you see that the first two terms are of the order 4. So this is something like the P Laplacian equation with p equal to 4. And again, here are the choices of the operators A, P, B, P, F, and G. So in this case, the operator A, P will be a non-local operator. Its action on the action of APU on V is given by this right-hand side, and the rest of the operators are just like in the P Laplacian case. Okay, so that's the subcritical case. So here is an extension of the abstract multiplicity result that you can apply even to the critical case. So suppose that so we're going back to the abstract operator equation. So assume the assumptions A1 through G4 on the operators A, P, B, P, F, and G. And assume that for each mu, there is some C mu, a positive number C mu, such that E satisfies the PSE condition below the level C mu. Then we can still get two critical points, two non-trivial critical points. If lambda is between 0 and lambda 1, assume that there is a W0 in M such that the functional on the ray joining the ray going through the point W0 is strictly smaller than C mu. The supremum of the function on the ray is strictly smaller than C mu for small mu. And if lambda is between lambda k and lambda k plus 1 for some k, assume there is a compact symmetric subset of the sublevel sets psi lambda with index k and a W0 in the complement of that set, such that if you look at the lines joining, basically if you take if you take points in C and form a linear combination like SV plus TW0 with S and T non-negative, then the supremum of E on that set is strictly smaller than C mu, again for small mu. Then the conclusion is that if mu is small enough, the operator equation will again have two non-trivial solutions, U1 and U2, with the energy of U2 positive and strictly smaller than C mu, if mu is small enough. So this can now be applied to the critical P-Laplacian problem. So here's the critical P-Laplacian problem. So F is as before, but now the Q is replaced with the critical exponent P star, and P is assumed to be smaller than N. So to state the multiplicity result for this problem, let me denote by sigma of negative delta P the Dirichlet spectrum of the negative Laplacian in omega. So this is a set of lambda such that this eigenvalue problem has a non-trivial solution. And let me denote by capital S the best Sobolev constant for the embedding of W1P0 omega in LP star omega. So again, the critical points of this functional are the solutions of our problem, and here's the multiplicity result for the critical case. So in the subcritical case, we didn't have any restrictions on N or P, and we also have any restrictions on lambda. It was just assumed to be positive. But here we do have some restrictions. So suppose n is bigger than or equal to p squared, and suppose lambda is not an eigenvalue of the negative P Laplacian. Then you can find a small enough mu and a kappa such that the problem has two non-trivial solutions, one with negative energy, one with positive energy, and the energy would be less than this right-hand side. So this 1 over n s to the n of p minus kappa mu is basically the threshold for compactness in this functional E. So the functional will satisfy the PSC condition if you are below this level with kappa sufficiently small. And then you can apply the abstract multiplicity result and show that this problem has two non-trivial solutions. And again, for the semilinear case, P equal to 2, this problem or this theorem was proved for the critical case in the paper that I just mentioned. But again, the method in that paper does not apply here because P is different from 2 now. Okay. Okay, so let me also just state the result for the fractional P Laplacian. So here's the corresponding critical problem for the fractional P Laplacian. So this negative delta SP is the fractional P Laplacian, and then you have the first two terms on the right hand side that are the same, and then the last term will be critical with respect to the fractional P Laplacian. So this fractional exponent is NP over n minus SP. So P is assumed to be less than n over S. S is between 0 and 1. And the assumptions on F are the same as before. Okay, so I'm almost out of time. So let me just skip the the setting of the problem and just state the multiplicity result. So here is the functional that corresponds to our fractional P-Laplacian problem. So you have this. So this is defined on the fractional Sobolev space WSP0, and again there are restrictions on NP and lambda. So n is assumed to be bigger than SP squared, and we assume that lambda is not an eigenvalue of the fractional P-Laplacian. And then the same conclusion as before holds, namely that you get two non-trivial solutions, one with negative energy, one with positive energy, and this right-hand side is now the threshold for compactness in the functional E. And you get two non-trivial solutions for sufficiently small mu0. Okay, so thank you for your attention.
Thank you for the Perera, very nice talk, very interesting talk. Thank you very much.
Thank you.
Any questions or comments? You can give questions in the dialogue that chat. You can also read there. You want someone else? I take someone, the listeners. Oh, maybe I ask a question.
Yes.
For fractional equations, fractional P-Laplace, and what are the main difficulties between the fractional and the no fractional?
Yeah. So the main difficulty is in estimating some of the integrals, because if you look at the first term of the functional, that you have this double integral over Rn cross Rn, and when you try to show that you can construct these sets C using this W0, where the functional is strictly smaller than the threshold for compactness, to get that estimate, you have to do more work to estimate that first non-local term. So that's one place where the additional difficulty comes in.
Non-local operator, yes.
Right. And then also the Talenti functions for the fractional P-Laplacian are still not known. So for the P-Laplacian, you know the minimizers in the Sobolev inequality in Rn, but for the fractional P-Laplacian, you don't know what they are, but you could still get around this difficulty by using some estimates for the Talenti functions. This was done in a paper with Marcos Cosina, Sundra Mosconi, and Yang. So that technique applies here.
And someone else, Professor Square, asked you, please give me a static PDE to solve values for content algebra in X, Y, Z, T for three-dimension problem. Give a static equation for boundary values. He asks you.
I'm sorry, I didn't hear it clear. Can you repeat that, please?
You can see what he write at the chat. There's a
on the chat.
Yeah. You can see that. The questions you can see.
Maybe he's asking what are the boundary conditions specifically for the specific problem, one of the specific problems you look at?
Oh, the boundary values are always taken to be the zero boundary values. So that's are the directly problems, but you can apply this to Neumann problems as well. The only thing that changes is that instead of working in W1P0, you'll be working in some other space, so W1P, for example, for the Neumann problem. But again, you can define the operators APBP in the same way. So this abstract multiplicity result applies even with other types of boundary conditions. So the only thing we'll need is that the boundary conditions will also have to be homogeneous of order p minus 1.
Yes. Any questions or comments? So
actually, I had one. We're speaking about also along the lines of the fractional equation. I was just wondering if instead of fractional P Laplacian, you had something with an integral kernel, possibly non-translation invariant, like some k of xy. Would this follow from a similar kind of technique, or is that a much more complicated problem?
I haven't thought about it, but so the question is, does this fit into the abstract operator equation setting? So if the operator defined in terms of this kernel satisfies the assumptions A1 through A4, then all this will apply. So just have to check those 4 conditions to make sure that they're satisfied.
Okay, so it's not like lack of translation invariance immediately rules out the whole thing.
Probably not. No.
That's interesting.
So
I can solve nonlinear partial differential equations, and I would like for each talk for the person to give a specific equation, and specific boundary values. All 0 is fine for boundary values, because I would like then to try my code and see if I get the correct solution for it. But you give me those general equations, I don't have something I can put into the computer to get a numerical solution of.
Yes.
Well, I mean, so if I may go back to my the slides again for a second. So see, so this first problem, I don't know if you can see my screen still. So this
not yet. No.
Not okay. So let me just share the screen again.
You can share the screen.
Okay, so this is the model problem. So you can, for example, take a p that's different from 2. For example, let's say take p equal to 4, and then pick a sigma that's smaller than 4. So let's say you take sigma to be 3 and q to be let's say 5. So suppose you're working in 3 dimensions. So that this is the critical case when q is equal to. So it's subcritical when q is less than 6. So you could try to do that problem. So you have specific values for p, sigma, and q, and you can take omega to be a ball, for example, and then you have this problem with specific values, and you can see if it has 2 solutions for small enough mu. And then no restrictions on lambda. So for example, you can take lambda to be 1.
Is u like the sine of x times the cosine of y and the arctangent of z? I want a specific equation. Numerically solve a specific equation, not a general equation.
So the specific equation is negative 4 Laplacian of u equals u to the power 4 plus mu u to u cube plus u to the power 5.
What value for mu?
Well, okay, yeah. So you need to plug in, let's say, small values of mu and see if you do get 2 solutions. I don't know how small it has to be.
Have you not worked a numerical solution?
No, I don't. No, I don't do numerical solutions.
Oh, okay.
Sorry.
Usually we here consider the usage, not. Yes. This is some different maybe. Okay, so we talk about very hard. Okay, so thank you the speaker and all the listeners again. We talk about, give a very nice talk, very interesting. So thank you here again. Thank you, Kanishka. Okay. See you.
Bye.
See you.
Bye.
See you, everyone. Tani. Okay.
Yes. Thanks, everybody.
Very good work, job.
Thank you.